So good afternoon, everyone. So today is the another day for Dr. Anwarul Abedin lecture series. So I welcome you all to this lecture series. I am Professor Mohibul Haq Bhuya, Department of Electrical and Electronic Engineering of American International University, Bangladesh. We have our respected Dean of Faculty of Engineering of AIUB, Professor Dr. ABM Siddiq Hossain, and our faculty members from the various departments of the under the Faculty of Engineering, and also our students. A very good morning to all of you and good evening for Dr. Masud, because he is in USA. Today we have all gathered to attend a webinar of Dr. Anwarul Abedin lecture series to commemorate the life of an outstanding individual and wisdom nurtured a dream into reality in an institution that has been providing quality higher education for around 3 decades, producing pioneering graduates, spearheading various job sectors that are spread across the globe. On this special day, we remember our founder chairman of American International University, Bangladesh, that was founded in 1994. The late Dr. Anwarul Abedin, who catalyzed substantial transformation in the educational sector of the country as an institution of moral and educational excellence. On this eventful day, we commemorate his values with an informative seminar on innovative technology that may well shape the future of technology and its advancements. Our today's session would be on future of computing and electronics in Internet of Things, wireless sensor network, and artificial intelligence era. Today, our distinguished speaker is Dr. Masud Hassan Chowdhury. He is the professor and division director of Division of Energy, Matter and Systems, School of Science and Engineering, University of Missouri, Kansas City, USA. Before start of his session, let us introduce our distinguished speaker through a short biography. Professor Dr. Masud Hassan Chowdhury received a BS degree in Electrical and Electronic Engineering from Bangladesh University of Engineering and Technology, Buet, Dhaka in 1998, and a PhD degree in Computer Engineering from the Northwestern University, Evanston, Illinois, USA in 2004. Currently, he is serving as the founding division director of the Division of Energy, Matter and Systems, EMS, under the newly formed School of Science and Engineering at the University of Missouri at Kansas City. Previously, he served as the Associate Dean of the School of Computing and Engineering for 5 years. He also served as the Department Chair and Professor of the Department of Computer Science and Electrical Engineering at the same university. Dr. Chowdhury served as the Chair and Chair-elect of the IEEE VLSI Systems and Applications Technical Committee from 2012 to 2016. He also served on the editorial boards of 5 leading journals published by IEEE, Springer, and LCBR. In addition, he has been serving the professional communities as a symposium chair, conference track chair, special session organizer, review committee chair, session chair, NSF, DOE, or NSERC panel member, and many other roles for the last 18 years. He traveled to more than 25 countries worldwide and presented over 100 invited speeches, keynotes, seminars, and conference papers. Dr. Chowdhury's research interests include post-silicon and beyond binary computing technologies, micro and nano devices, circuits for flexible systems, transparent and wearable electronics, and nanotechnologies for biodegradable electronics, sensing, biomedical, and energy applications. He has published 2 books, 2 book chapters, 183 journal and conference papers, supervised 15 PhD theses, 11 master's theses, 36 master's projects, 25 undergraduate research projects and senior design projects, and 5 high school student also. Dr. Chowdhury has been a distinguished mentor for the young and early career faculty members at UMKC. He mentored 9 assistant professors and 1 postdoctoral research fellow. He received the Leadership Excellence Achievement Program LEAP Award in 2017 from the Missouri City of Professional Engineers. He developed 8 courses in the areas of microelectronics and nanotechnologies. And also he is involved in developing or upgrading more than 12 of undergraduate and graduate degree programs. He received the 2009 UIC College of Engineering Teaching Award for demonstrating excellence in teaching, curriculum development, and student advising. In 2019, Dr. Chowdhury was nominated for the University of Missouri Systems Manual T. Paccio Leadership Development Program LDP to recognize his leadership aspirations and achievements. In 2013, he was selected for the University of Missouri System Faculty Scholar UMFS program. So this is the short biography of Dr. Chowdhury. So now I would like to invite Dr. Chowdhury to
This meeting is being recorded.
Start his presentation or talk. So thank you all for joining with us.
First of all,
I have to unshare the slide so that.
Yeah.
Oh.
Can you see my slide?
Oh, we can see. Okay.
Yeah. First of all, I like to thank you all in AIUB for giving me this great opportunity to speak to you. I have been fortunate to travel all over the world. However, always it is most satisfying and humbling experience when I get the opportunity to talk to the people from my own country, because any kind of recognition from your near and dear one is actually the most satisfying. And particularly today, I'm extremely happy to see my undergraduate advisor at BUET, Dr. Siddiqui, your dean. He was the first faculty member I met when I started my BUET life in 1993. And also, I'm very happy to see my dear friend Mohibul after so many years. We were in the same section, same class, and we had many good memories. So with no further delay, I want to introduce today's talk. And at the end of this talk, I also have some slides about some of the information about my university and also some of my vision as a academic leader. And I would like to share those if time permits, so that we can talk about collaboration, we can talk about programs that we can develop together. So in this presentation, I'm going to talk about the technological development, the remarkable technological development that actually enabled us this era of Internet of Things, wireless sensor network, and artificial intelligence. Those technologies and these new areas like IoT, WSN, and AI have transformed the entire modern human civilization and the way we live our life. And this type of changes was beyond the imagination of our prior generation. Now, let us look at some of the trends and technological developments that actually took us to where we are. So if we look at what is happening in broadband communication era, across the globe, internet and telecommunication traffic volume is increasing 50 to 60% a year. And with that, the ICT energy consumption, ICT sector's energy consumption is increasing by more than 100% in every decade, but now actually it is increasing by almost 1,000% every 5 years. So now the question is, what is the consequence of this tremendous amount of energy that is consumed by the ICT sector? It is leading to another global, it is making our life easier, but it is making our world, our planet, a very vulnerable one, simply because this tremendous amount of energy is leading to some global challenges like climate change. Now let us see the consequence of this energy consumption in ICT sector. Today, over close to 10% of the global electricity is consumed by the ICT sector. In 2012, it was 4.7%. Now, in 2014, the total energy consumed by only the US data centers was around 70 billion kilowatt. And by 2020, it reached to 140 billion kilowatt hour of electricity just by the ICT infrastructure in the United States. Only the office area network, the LAN routers and switches across United States consumed 229 megawatts of electricity in 2012. Now, we have become completely dependent on Google search. Every time we are entering a Google search, we are consuming 0.003 kilowatt hours of energy. It seems like it's a very small energy, but we are talking about trillions of Google search every day all over the world. If you now collect all the energy consumed by just by Google search, you can think about the amount of carbon monoxide it is injecting into our environment. And one estimate says that the ICT sector producing 200 million tons of carbon dioxide annually into the air. And if you want to absorb those carbon dioxide, 250 million tons, you have to convert every square inch of entire United Kingdom, Britain, Scotland, Wales, all together, entire United Kingdom, if you convert every square inch into dense forest, only then you can absorb that amount of carbon dioxide emitted by this ICT sector. And by next 1 decade, they are projecting that the total energy consumed by ICT sector would reach to 1,500 terawatts of power. 1,500 terawatts of power, that is several thousand times of the total power consumption for a country like Bangladesh. So what is the technological goal and targets for people like us in the scientific community, particularly those who are in the engineering and computing field? We have to develop technology, particularly electronic and computing technologies, where energy consumption can be reduced by a factor of 1,000, not like 5 times, 10 times, by a factor of 1,000 in the next decade. Only then we can control some of these carbon dioxide emission into the environment and the enormous amount of energy consumed by ICT sector. Now let us see what are the components of ICT sectors that are leading to this energy consumption and carbon dioxide emission. Of course, our internet and ICT backbones are data centers. And then together with, now we have completely dependent on mobile infrastructure. That is the second biggest component of this energy consumption. And we have millions of electronic and computing office equipment. And in addition to mobile infrastructure, like all those towers and LNVs, now each one of us, we have on average 3 mobile or portable devices, cell phone, tablets, video games, laptops, and all other things. So in all of these ICT components, one of the biggest challenge and threat for the scientists and engineers is the reduction of standby power consumption. So that is the biggest technological challenge, to minimize or suppress power consumption when we are not using the device, rather than when we are using the device. When we are using the device, we are not worried about the energy consumption during that stage. We need that power, but the problem is, the biggest problem we are facing is the power that we are consuming during the standby mode or sleep mode, or when we are not doing anything. If we can attack that component, minimize or reduce or eliminate that part, that will lead to a tremendous amount of energy saving and efficiency increase for all the different components of ICT sector. These are some of the basically breakdown of data in terms of different components of ICT sectors, in terms of power consumption and carbon dioxide emission, and these are related some of the technological data. Now, if we go inside the chip that is running all these data centers or mobile infrastructure or portable device or computing device or office equipment, if we inside the microprocessor that is powering all those ICT components, if we look at this, 60 to 70% of the chip area and power consumption is coming from the cache memory. And this cache memory is made of mostly 60 SRAM. And this 60 SRAM is based on CMOS technology, which is very vulnerable to noise and inefficient in terms of energy consumption. So we have to look for something beyond CMOS in near future. And these are some of the newer direction that computing and electronic industry will move to, as predicted by all the major funding agencies of United States government. And one of the new direction is terahertz electronics. As we are becoming dependent on satellite communication, as we are becoming dependent on extremely high frequency sub-millimeter electronics for specialized application, ultra high band, broadband communication, and very high efficiency, high power, and robust data centers. For all those, we need electronics and computing device that need to be operated at terahertz frequency. We are talking about in the range of 500 gigahertz to several thousand gigahertz, terahertz frequency range. Then wireless sensor network and IoT is becoming another widely spreading sector, because our healthcare industry, our consumer industry, our everything we have, all the home appliance devices and everything else, entertainment devices, now they are dependent on even the environmental sensors and monitors we use for geographical scanning of environmental and climate situation. All those sensors, they are working wirelessly, and there are thousands of IoT devices embedded in all those wireless application devices. We are not just talking about smartphone and tablets. There are thousands of wireless devices working all around us. We don't see them. And inside all those devices, there are thousands of IoT applications. So one of the key requirements for these wireless sensor networks and IoT devices, this must be operated at ultra low power region, because they're dependent mostly on stored battery energy. So because they're portable, they're embedded, and you cannot plug and play every time to supply energy, particularly if it is in a remote location. And most of the time, if it is in a remote location, it has to depend on the energy harvested from solar energy or environment, thermal energy or vibration energy or somewhere. Let's say you have an embedded sensor inside your artery of the heart, sending signal from the stent you have inserted inside your artery. That sensor, IoT sensor, that wireless sensor must collect the energy from body temperature or from body vibration. And that has to be operated at extremely low power range, which cannot be designed using conventional CMOS transistor, because CMOS transistor and CMOS technology is confined at the mid power, mid performance range. So if we look at the overall micro and nano electronic and computing technologies, and if you draw a simple curve, in y-axis we put power, on the x-axis we put performance, speed or frequency, the CMOS technology-based silicon and binary computing-based platforms, we are stuck in the mid-performance and mid-power range, right at the middle of this curve. Why is that? Because if we want to increase energy efficiency, we have to do it at the expense of speed. We have to slow down the system. If we want to increase the frequency or speed up our system, we have to do it at the expense of higher energy consumption. CMOS technology has two opposite competing goals. If you want to speed up, you have to spend more energy. If you want to achieve higher energy efficiency, you have to sacrifice speed. However, as I just mentioned, in the wireless and IoT sector, we need devices that can be operated at ULP range, ultra low power range, where speed is not critical. However, the energy efficiency, extremely low power consumption is very critical requirement. And then terahertz frequency, which I showed earlier, that does not care about energy consumption. When you are talking about a satellite communication globally, you don't care about energy consumption. You want to make sure that your communication channel, that wireless satellite-based communication channel, is reliable and robust. You care about speed and frequency. So, and you will have those type of application where energy consumption is a secondary issue. Performance, reliability, and frequency will be the ultimate requirement. But we as a scientists and engineers, can we go to an ideal utopian world where we can operate those high frequency application with ultra low power consumption? That would be the future, long-term future direction on the bottom right corner of the screen, high frequency at low power. That would be the ideal destination, but practically with the current available technologies, it would be impossible to achieve that ideal or utopian dream of scientists, that is high frequency at ultra low power consumption. So we are now moving to the top right, ultra high frequency, or left bottom, ultra low power application, for one for the terahertz electronics, one for the wireless sensor network and IoT devices. But the problem is, even for ultra high frequency and ultra low power ranges, currently CMOS technology is reaching its material and technological limit. And von Neumann computing architecture has a fundamental bottleneck called memory wall. In addition to that, interconnect and bandwidth limitation due to this memory wall is limiting what frequency we can achieve. For example, theoretically, even the current Intel FinFET 18 nanometer technology, theoretically, if we just consider the transistor itself, we can achieve 50 to 100 gigahertz. But practically, the Intel's FinFET 18 nanometer based microprocessor are marketed at below 4 gigahertz. Why is that? Because the Within the von Neumann computing architecture, this memory wall or interconnect and bandwidth limitation will limit our ability to achieve higher frequency that can theoretically be offered by the 18 nanometer FinFET technology. So we'll look into this later. And one message I want to give, that overcoming the Boltzmann tyranny, which is dictated by the material limit or fundamental physics of silicon and CMOS device, overcoming this tyranny or bottleneck, using CMOS device and silicon technology will be impossible. So you have to look for newer technology and newer physics. So these are some of the trends that are going on in microprocessor and interconnect technology world. So one good thing is, over the last 7 decades, microprocessor technology advanced so much that the cost per function, logic function implementation has gone down exponentially. Otherwise, if it didn't go down exponentially, we had to pay $300,000 for a 1 gigabyte memory. If we compare it with the price production cost of per bytes of memory in 1991. However, now you can drive a flash drive of 1 gigabytes or more with less than $10, right? Because technology progressed so much that the per byte memory bit cost or per logic operation implementation cost into actual silicon chip, and this remarkable development and growth became possible due to the prediction of a visionary person, Michael Gordon Moore, the founder of Intel. And that prediction, it's not a mathematical law, it's not a physical formula that can be proved. It's just a prediction, it's just an extrapolation of his observation of first 5 years of IC industry from 1962 to 1967. Based on that, he gave this remarkable prediction that later became Moore's law, and Moore's law became the guiding line, kind of the guideline for IC industry in the next 6-7 decades. But that is now hitting the wall, and we are reaching the material and technological limit. So these are some of the things that is going on in the technology world. When IC industry started in early 60s, the transistor length, the size of the technology, also known as the transistor length. For the student, if anybody asks, what do you mean by 18 nanometer technology? We are talking about the length of the transistor, the distance between source and the drain. The length of the transistor is called technology size. Since we are increasing more and more functionality into our microprocessor, we need to put more transistor to implement those logic function. And only way we can implement those logic function is by putting more transistor inside the chip. The problem is the chip is made of silicon, and you cannot make the chip larger to put more transistor. Why? Because the chip is made of silicon, and silicon is a fragile material. You cannot make the dimension of silicon chip more than 3 centimeter in one side. If you make it more than 3 centimeter in one side, it will break down. It will not physically sustain. So the maximum area for a chip you have for the last 70 years is 3 centimeter by 3 centimeter. Even they don't go up to 9 square centimeter 3 by 3. They try to remain within maximum 6 square centimeter. So within 6 square centimeter real estate space, if you want to implement more function, you need more transistor. And only way you can do it if you can reduce the size of the transistor. That's why in 1962, we started with transistor of the size of 10 to 20,000 nanometer, 10 to 20,000 nanometer. Today, we are talking about 10 to 18 nanometer. So what is the consequence of technology scaling or sizing down of the transistor? We are able to put more function. However, at the same time, we are becoming dependent on portable and wireless application. And those portable and wireless applications are mostly dependent on battery stored power. So we have to reduce the energy consumption so that smaller battery can support our portable device for longer time. So we have to reduce the supply voltage. So earlier generation in 1960s, ICs were operated in the range of 15 to 20 volt, and gradually now we have come down to 0.9 volt to 1.1 volt range. Why? Because if we operate billions of transistors with 15 volt supply, you will burn the IC in a fraction of a second. Your IC cannot sustain that amount of energy with so much transistor and with so high voltage. So we have to reduce the voltage supply so that each transistor, smaller transistor, can be operated at a much lower voltage. So it will consume much lower power. As a whole, your chip temperature will remain within the tolerable limit. So those are but the problem is now we are scaling the transistor size so much that it is now reaching the material limit, and also total aggregate amount of energy consumption and thermal temperature this enormous amount of transistors are producing, it is going beyond the physical and material tolerance limit of silicon and other material used in chip fabrication. So just I brought this slide to give the students an idea about diagram of a MOSFET transistor. Those red areas are source and the drain. The distance between source and the drain, that is called length of the transistor L. If that length is 18 nanometer, we call it 18 nanometer technology. If that nanometer is 5 nanometer, this L length is 5 nanometer, we call it 5 nanometer technology. So one of the biggest problems with the current transistor technology based on silicon and CMOS structure is we are applying the voltage at the transistor from the top, called gate terminal, to turn on and off the transistor. But that is limiting our ability to turn on the transistor with a lower voltage, because the way we turn on a transistor, we apply an electrical field to turn on the transistor. So the designer thought that if we can apply the gate voltage from the top and from the bottom, then we can turn this transistor on with a much smaller voltage. That led to the introduction of dual gate transistor. Now then they thought that how about raising the transistor vertically and applying the gate voltage from the left and from the right, or all around that tower-shaped transistor channel. Then we can apply an extremely high strength electrical field from all around the transistor channel, so it can be turned on at a much smaller voltage. So we can reduce the energy consumption and operating voltage much lower. That actually led to the introduction of FinFET, where the transistor channel rising above the body of the transistor like a fin on the back of a fish, and you are applying the voltage all around from the left side, right side, and the top side of that fin, so that you can turn on that transistor channel with significantly lower voltage. That is actually the current generation of microprocessor technology, but still that is based on silicon and MOSFET technology. So now people are thinking, how about creating a transistor channel like a cylindrical wire and apply the gate cylindrically all around the wire? That means the channel is like a nano size wire, and the gate will wrap around that nano wire. It's called gate all around device. Now in a FinFET, I am able to apply the gate voltage from the left or from the right so that I can turn it on earlier at a lower voltage. But what if the channel itself is a cylindrical wire and I can wrap the gate like an additional material layer around the channel and apply the gate voltage from all sides circularly? Then we can turn on the transistor at a much lower voltage, even lower than the FinFET. That led to the introduction of the newer device called nanowire device, also known as gate all around device. And that is the current technology at the experimental stage in academic labs and industrial labs across United States and the developed countries. And there are lots of prototype chips already fabricated, but they're expecting that next technology based on silicon will be gate all around device or nanowire device. It is already proven and working in the experimental level, but they are going to introduce it commercially most likely within a decade. But one of the fundamental problems with all of this device, including gate all around device, is the physics of the MOSFET transistor itself, whether it's a regular conventional MOSFET or gate all around MOSFET. There is a parameter called subthreshold swing. Let's not go to the detailed device physics. This subthreshold swing is denoted by S. It is the minimum possible theoretical value for silicon-based MOSFET transistor of any structure, including gate all around structure, is 60 millivolt per decade. That means for 1 decade in log scale, 1 decade increase of current, you need to apply minimum 60 millivolt voltage. You cannot go beyond that. So for every decade of current, you have to apply minimum 60 millivolt voltage at the gate. What is the meaning, interpretation of that? The amount of logic you want to implement, amount of function you want to implement with your laptop or smartphone is directly related to the amount of current it is drawing. So if you can deliver that current your smartphone is asking for with lower amount of voltage, that means your device, your battery, your device is becoming more energy efficient, and you can run your smartphone with the same battery for 3 days, 4 days, 5 days. If you can lower this S value to, let's say, 20 millivolt per decade, that means your smartphone battery will run 3 times or 3 days. If you currently can run 1 day with 1 charge, you can run it 3 days because you are lowering the amount of voltage needed for the amount of current you are generating. Simple Ohm's law. So now every research project in semiconductor device area, they have one single target, whether it's a graphene-based device or other new emerging semiconductor-based device or newer type of technology. Everyone is targeting one thing: can I lower the S value from 60 millivolt per decade, which is the theoretical minimum for MOSFET technology and silicon. US federal agencies, they have a target to reach 20 millivolt per decade. That's why I mentioned that number, 20 millivolt per decade. That means if you can reach that number, everything we are running, all the wireless portable devices can run 3 times longer for the same amount of charge, or you can minimize the size of the battery if you want to still run for the same amount of time. That will be a huge improvement for everything we use. And that will be a huge impact on global climate problem due to the carbon dioxide emission, which is coming out of ICT sector energy consumption. But currently, where we stand in the CMOS technology world, I said 60 millivolt per decade is the theoretical limit, but actually everything we are using currently in the present day, we are actually around 80 millivolt per decade, because remember, 60 millivolt per decade is the theoretical minimum. If we add all the interconnect issue, all the parasitic issue, and all other non-ideal factors which are not in our control, the actually what we are achieving is between 80 to 100 millivolt per decade. That is much higher than 60 millivolt per decade. This limit of theoretical limit of 60 millivolt per decade, that is known as Boltzmann tyranny. Why it is called Boltzmann tyranny? Because it is this value of 60 millivolt per decade is determined by a technology constant called Boltzmann constant. It's a fundamental physics constant of silicon material. Now, let us move to some of the emerging direction. In the ultra low power range, people are exploring several new directions to overcome this limitation of silicon and CMOS technology. FinFET is the current one, but it still is CMOS. They are now looking at nanowire device. There is another possibility, but still it's silicon based. So they're looking for non-silicon based nanowire. But two of the new emerging direction are, one is called negative capacitance based field effect transistor, and that is same CMOS structure but new material. So research are going on in two different directions. One group of researchers are looking for new materials other than silicon. One group of researchers are looking for new transistor technology other than CMOS or MOSFET. So on the technology front, people are looking at band-to-band tunneling device, the new physics for the transistor. And on the material side, people are looking for technology like negative capacitance-based field effect transistor. And some of the newer materials people are looking into 2D nanomaterials to replace silicon, like graphene and molybdenum disulfide. And also a new class of material people are now exploring is called metal insulator transition material, MIT materials. And there is a huge new section that is emerging. That sector of technology is called, one of them is transparent electronics. I can see through my laptop screen. On the other side of the screen, it will be purely transparent. Or I can roll my cell phone, entire cell phone or laptop or TV screen, flexible electronics. So people are exploring different materials like zinc oxide, indium oxide, cadmium oxide, and all those things for transparent and flexible electronics. Now, so far we talked about technology and material. What is alternative to CMOS technology? What are the alternatives to silicon as a material? But we have to now look into the fundamentals of computing itself. The current computing world is based on von Neumann computing model, and everything we do in the digital world, we are dependent on binary logic system. The entire digital world is dependent on binary logic system, and all the computing architecture is based on von Neumann computing model. So von Neumann computing model has a serious limitation. The limitation is the memory unit and the ALU unit, they are separate. And the communication between memory unit and ALU unit is limited by the bandwidth of the bus between memory and the ALU. Now, all of you know, when Windows is marketing their newer version, they're saying that, or Intel is marketing new microprocessor, They're saying that it is 64-bit architecture, 128-bit architecture, 256-bit architecture. What does it mean? The bandwidth of the bus that is between of the bus between memory and ALU is 256-bit line for a 256-bit architecture. That means you can transfer only 256 binary bit at a time in a time period between memory and ALU. While your memory is in the gigabyte size, your ALU is running at gigahertz frequency. But you can only transfer 256 bit at a time. So as you can see, you can store terabytes of cache memory data. You have ALU that can run at terahertz frequency. But the problem is, since they are separated from each other by a data bus, which in the current technology can go up to maximum 256 bit. That's why the Windows are 256 bit, the architectures are 256 bit. So that means memory can be operated at gigahertz, can store gigahertz, gigabytes or terabytes of information. ALU can operate at terahertz frequency, but you don't have actually enough bandwidth to supply the data to utilize your capability of the ALU. So that is actually killing all the computing power which we can theoretically achieve. So what is the alternate path forward? That means we have to think beyond binary logic. We have to think beyond von Neumann computing model. So at any time, please, you can stop me, ask question. So first, look at some of the limitation, as I already mentioned. On the left side, I am showing you von Neumann computer architecture, where memory and digital logics, they are separated, and then you have separate control block, you have separate IO block. What if current computers can act like a human brain? What is human brain functionality? Every cell inside our brain, they are storage unit. They can store information. They can also process information. Inside our memory, inside our brain, we don't have a separate section for memory. We don't have a separate section for processing. Every part of our brain is actually storing and processing certain types of information and decision about our emotion, about our logical thinking, analytical thinking. It's controlled by about the control of our organs. Is distributed in different parts of our brain, but each part of the brain is individually storing information regarding the function it is assigned to. At the same time, it is processing the information and making the decision about the function assigned to that part of the brain. If we can develop a computing model by merging or breaking down the von Neumann computing architecture, that leads to the new field of computing called human brain-like computing, which is also known as officially neuromorphic computing, where same functional unit, same logic unit can perform dual function. At one time, it will be a memory. At the same time, it will be also used as the logic processing or decision-making cell. And those human brain-like computing must be operated at ultra low power range, because if you think about the density of cell we have in our brain, every cubic centimeter has several billion brain cells. So if we want to mimic a computing power of our human brain, and you want to utilize a computer very similar the way our brain works, the amount of transistor cells who will do the dual purpose logic processing as well as information storing, we are talking about trillions of transistors compressed in a tiny area. And if we do not reduce per transistor energy consumption to extremely ultra low power range, you cannot build those chips. The other option is, along with brain-like computing, can we move out of binary logic? Currently, if you have a two variable binary function, input A and input B, how many different sets of information you can express by two variables binary problem? Binary base 2, you have two variables, 2 to the power 2. You can express 4 different combinations of binary value, 00, 10, 01, 11. This 4 binary combination can be interpreted as 4 pieces of information. But if you can implement a ternary logic base 3 with the same 2 bits, you can express how many different sets of information? 3 to the power 2, 9 different sets of information, because each bit now can have 3 different values, 0, 1, 2, or -1, 0, +1. In binary, you can have only, every bit can have only 2 values, 0 and 1. Then if you move to quaternary logic, for 2 bits, you can store 4 to the power 2, 16 different sets of information. That means moving from base 2 binary to base 3 to base 4, every time you move up the base, you are increasing your storage and signal processing capability exponentially in the power, not linearly. So that is the next direction, another next direction of research. One part, human brain-like computing. The other part is multivalue logic. Why we need that? Because we are becoming completely dependent on data we gather every day, the data we store every day, and the way we process and interpret those data to make everyday decision, from personal life to professional life to industrial sector to government sector to private sector. It's all data dependent. So the volume and amount of data that need to be stored, processed, and interpreted and applied is increasing exponentially every day, and that cannot be handled in near future by binary or base 2 system or von Neumann computing model. And that's where people are exploring this newer direction, like human brain-like computing or multivalue logic and multivalue memory technologies. Now, recently, just less than 10 years ago, US federal agencies and Semiconductor Research Corporation, which is the consortium of all the leading semiconductor companies like Intel, IBM, Micron, Qualcomm, and all those big players together, and all the leading academic institute, they have this organization to exchange views and ideas about and determine the future directions of technology. That is called Semiconductor Research Corporation. Together with United States Federal Funding Agency, they introduce this new area that is called semiconductor synthetic biology, semi-syn-bio. The idea is similarly to mimic the computational power, information processing power of our human body cells. On average, it is predicted that our human body every day, from head to toe, we are generating 40 exabyte of data in our brain through all the organs and subsidiary organs and arteries and all the sensory systems of our body. And these data, these 40 exabytes of data, they are processed by our brain, stored by our brain, and every single cell in our body, they are producing this information through our DNA, activity of our DNA. So now scientists are thinking, can we express information in terms of different states of DNA by utilizing those biological cells as the computing device. Instead of currently everything we are doing in the electronics and computing world, we are measuring information in terms of different levels of voltage. What is binary 0? What is binary 1? These are different levels of electrical voltage, electrical signal. What if we can express information as a biological state, state of DNA, phase of DNA in a biological cell? Because every DNA in every DNA string, in every human cell, can have many, many different states. That's how we are producing 40 exabytes of data every day, our body. So that is a very, very brand new branch of research where DNA states of biological cells will be used as a computational device, fundamental computational device that is a marriage between biological science, computing technology, and electronics and semiconductor. That is called semi-syn bio. Now, let us move to a completely different direction. Before moving to some of the new multidisciplinary research related to our planet and our human civilization, where we as the engineers and scientists, we can contribute, I want to take a pause and I will request if anyone from audience, if they want to ask any question on the first part of the presentation.
The audience, do you have any question? If you have any question, you can ask by yourself or you can write your question in the chat box. I think Dr. Masud, you can continue.
Okay, then we will give time for question and answer at the end then.
In the end, we can.
Yeah. Oh, okay. So, but you just remind me. I have time, but if you have time limitation, just remind me.
Yeah. Okay, so you continue. I think you can finish it within half an hour.
Yeah, definitely.
Okay.
Okay. So now let us look at some of the consequences of our modern lifestyle and how those lifestyle are affecting our planet and our civilization. So two of the biggest threats for modern human civilization are electronic waste and single-use plastic. These are the impact of our modern lifestyle. Every single day, millions of pieces of unused electronics, like the cell phone you no longer use, the laptop you no longer use, the desktop you no longer use, you are dumping it. And those electronic waste are going to environment, some landfill. And single-use plastic, every day we are using plastics everywhere, and over 90% of the plastics we use are single-use. That means we discard them right after first use. Now, to overcome these global challenges and threat to human civilization, what we can do? Two of the newer research direction are, one of them is biodegradable electronics, mechanical device, and plastic. It's a huge education and research opportunity for us. Then if we dispose it to environment, it will dissolve itself safely into the environment if it is biodegradable. The second very important the research and education opportunity is, can we use this electronic waste as the secondary source of rare material instead of throwing them into disposal or garbage bin or in the landfill? A related third new opportunity for education and research community is, can we convert our manufacturing and business processes reversible? That means green. That means everything we use can we reverse the process to reuse it after we are done with their application? With all these changes, there is another parallel global crisis that will become the biggest threat for human civilization. This is already a big threat for human civilization. That is the crisis of sweet drinking usable water. And that leads to the crisis of diminishing fish stock. That is also an impact of our modern lifestyle. With all these changes, and earlier we mentioned about carbon dioxide emission, one sector we can focus on, that is the automobile sector, that is producing enormous amount of carbon dioxide, carbon monoxide, and many other poisonous gas. That is the automobile sector. So another opportunity for us to focus on the electrical vehicle and emerging battery technologies that will not be dependent on toxic acid and hazardous material. Because global proliferation of ICT sectors is making this carbon dioxide emission and energy crisis even worse every day. So global community can, particularly the academic community, they can come together and develop multidisciplinary research innovation test bed to address some of these global challenges. And I will elaborate on few of these in the next few slides, and then I will stop. So as I mentioned, electronic waste. In 2019, we produced as a human civilization 53.6 million metric tons of electronic waste by throwing our unused laptops, smartphones, or all the electronic devices. On average, 8 billion population across the world, on average, each of us, we have produced 7.3 kilogram or 16 pound of electronic waste in 2019. Only 17% of this is collected and recycled, remaining 83% just thrown into the water, landfill, and environment. Now, let us look at the plastic situation. Since 1960s, our use of plastic increased by 20-fold. 95% of this plastic are lost from our economy, from our use, just after first use. We are talking about 5 to 13 million tons of plastic thrown into our ocean bed, river bed every year. Out of all the plastics we are producing, only 6% are recycled in Europe. Europe, by the way, is the best in terms of recycling. If the best region is only recycling 6%, now think about Asia, Africa, United States, and South America, how much actually plastic they're recycling. They're recycling less than 6%. Remaining over 95% are thrown into land, water, and other parts of the environment. If we can collect all those discarded plastic, we can save, actually, we can reduce 400 million tons of carbon dioxide from throwing into environment, because a major portion of the plastic across the globe, particularly in the developing countries and underdeveloped countries, they're just burning those plastic. By burning or incinerating plastic, we are throwing 400 million tons of carbon dioxide per year into the environment. This is a United Nations report. This is showing different areas of the globe that is contributing to this 53.6 million tons of electronic waste every year. It is divided into different zones. As you can see, the worst offender is Asia, 24.9 million tons because of the population and also because of the lower awareness. And this is basically a division of plastic waste by country, different country. In Europe all alone, what are the different sectors that is contributing to this plastic crisis. So there is one study of European Union showing that if we can save all the plastic or recycle or reuse all the plastic across the globe, it will save 3.5 billion barrels of oil per year, because hydrocarbon, methane, and petroleum is the raw material for plastics we use. So if we can recycle every single piece of plastic, that will save 3.5 billion barrels of oil per year, which is equivalent to 100 years of oil consumption by a country like Bangladesh. Now, as a research community, what we can do? Earlier I mentioned that we can work on biodegradable polymers and materials for electronic and plastic industry. To give you a perspective how serious this crisis is, in the current electronic industry, we are using 69 different elements out of 115 in the periodic tables. I hope all of you remember chemistry periodic tables. We have between 105 to 115 different elements, material in the periodic table. Out of those 110 plus materials, electronic and computing industry use 69 different elements in the periodic table, and majority of those 69 elements, other than copper and aluminum, are identified as rare earth materials or critical materials. That means they are very limited in supply and they are available only in the few regions across the globe. So if we can recover some of those rare earth materials from the electronic waste and reuse it, that will be worth of 60 billion US dollar. That means that will be 3 times more than total market value of global silver industry in terms of GDP, as United Nations reported. So if we can find materials and technologies to develop transient and biodegradable electronics. The biodegradable electronics are also called transient electronics because it will degrade into environment when you throw it. So it will dissolve into the water or land safely. And there are lots of material level research and innovation going on all over the world just to find technologies and materials for transient and biodegradable electronics. That's a good news. If researcher they find materials suitable for particularly organic materials and naturally synthesizable materials for this biodegradable electronics, that would be a huge achievement for our civilization. One interesting thing is that the single-use plastic problem and this electronic waste problem, they're correlated, because in addition to our day-to-day consumer industry, one of the biggest user of plastic product, polymer product, is the IC industry, the computing industry. So if we can find biodegradable plastic, that will lead to our ability to implement biodegradable electronics and computing devices. So that's a huge opportunity for us as a scientists and engineers to do research on. These are some of the potential applications of the early stage researcher identified for transient and biodegradable electronics. As I mentioned, there are many carbon and non-carbon based materials and polymers that are being explored for plastic industry. They can be used for electronic application. Some of those are explored for electronic application, can also be used for plastic and polymer applications. So there is a link, and we can actually address both challenges. We can address actually both challenges at the same time. if we get into this type of research. So now let me then quickly go through this one. Due to the global water crisis across the globe, one child is dying every 2 minutes just because of drinking dirty water. There are 2.2 billion people across the globe. They do not have access to clean water. Even developed countries like United States are now facing tremendous water shortage. There is a river called Colorado River that supplies water to 5 of the biggest states of United States: California, Arizona, Utah, New Mexico, Texas, and Colorado. 6. Now that Colorado River is drying, and these 6 most developed states are now under tremendous threat, what they will do after 10 years, 20 years, now that the Colorado River is drying and all the lakes that are supported by Colorado River are drying, and they have developed so many different cities and industrial areas, they will not have waters to sustain those cities and industrial areas. And this dirty water or lack of water is leading to another biggest crisis called water sanitation and hygiene crisis. This is actually pushing many of the communities to the edge of existence because of this water sanitation and hygiene crisis, because those are leading to many different types of infectious diseases. Globally, there are many foundations you as a researcher and scientist, you can approach to actually pursue research in this WASH sector, known as WASH is the short end of water sanitation and hygiene. From Green Water Foundation to Hilton Foundation to Bill Gates Foundation to Coca-Cola Foundation, there are many, many foundations all over the world. They are funding this particular research area just to address the global water crisis. Now, what you as an engineer and scientist, someone from Faculty of Engineering can do, because water purification and sanitation now is heavily dependent on AI and machine learning based data analysis and finding solutions based on our human lifestyle, assessing water crisis using AI and machine learning based technique, and also utilizing different types of sensors to identify the extent of pollution, to identify the extent of water related crisis. So this is not something for people in the environmental science sector. This is an area where arts, humanities, engineers, and environmental scientists, even all the people from healthcare industry and biomedical industry can work together to find a solution for this global crisis. Now, the new direction. We are now moving, first we moved away from fossil fuel based automobile to hybrid automobile. Now we are talking about fully electric automobile to completely eliminate the exhaustion system of our cars. So this is the biggest threat, the biggest challenge for electric vehicle technology is the limitation of the battery technology. So when we are talking about electric vehicle technology, everything else, super efficient motor, sensor, automotive driving system, everything is there and matured. But the only reason the automobile industry cannot develop a car that can run 500 mile, 1000 mile after single charge, simply because of the limitation of the battery technology. There are many new different battery technologies and battery materials are being explored by the engineers and scientists in both academic organization and industrial organization like General Motors. But still, there is a huge opportunity and room for new invention. Currently, automobile industry, they have to spend $1,200, $900 to $1,200 for every kilowatt hours of charge to be stored in the battery. That is either making the car very expensive or the battery size is so large that it is actually becoming larger than the car itself. That's why they are not able to put high mileage per charge. Now, EV industry, electric vehicle industry, they want to come down to, in the next 1 decade, $250 per kilowatt of energy. That will need a radical change in the battery design, battery material, and battery technology. Ultimately, in the next 2 decades, if they can reach $100 per kilowatt target, then the electric vehicle will be cheaper than the Toyota, Honda, Nissan, or whatever car you are driving today. Now, I will end with this particular slide. Now that we are becoming dependent on internet, we are dependent on cloud-based cyberspace. So our personal, organizational, and national security are becoming dependent on the resilience of cloud-based cyber infrastructure. So cyber security and hardware security, those will be very, very critical issue for the research community, for the academic community. In the United States, all the federal agencies are now funding to identify and analyze from the behavioral aspect to the technology aspect of cybersecurity. Interestingly, one of the biggest group of researcher in cybersecurity and cloud space, they are not actually engineers. They are people from psychology, behavioral science, humanities, because it is our behavior, it is our lifestyle, it is the way we do things and do things on our internet-based device that is actually affecting how cybersecurity engineers and scientists can actually plan this whole cybersecurity system. Because people who have no clue, no idea about the whole issue of cybersecurity, they are actually the most vulnerable points for the cybersecurity community. So to actually address and resolve the problem of cybersecurity, problem of personal privacy, national and organizational data security, we have to actually analyze the behavior and lifestyle of people who are not familiar with engineering and the scientific side of cybersecurity, because they are the main threat, because they are sharing the data, they're using the internet infrastructure in a way that is making it very vulnerable for everyone else. So this is an area where arts and humanities and everyone else from science and engineering community can collaborate together. I think, yeah, this is the last one. Since you are also a College of Faculty of Engineering, you have people who would be interested in biomedical engineering. But when you talk about biomedical engineering, and then you have computer science, in between biomedical engineering and pure computer science and computer engineering, you have bioinformatics, you have genomics, genetic engineering. So entire, let's say, for example, entire healthcare industry is now dependent on analysis of infection, human reaction, and potential drug. It is actually one of the most biggest application of AI-based data analytics. So in developed world, one of the largest or rapidly expanding area of research is bioinformatics and health informatics, also genomics. These are related. This is one big area. So, and these are the areas where people from engineering, computer science, and biological science area, they can come together and do research. As I mentioned, future will be dependent on smart AI-based analysis of the symptoms, infections, and potential treatment. And that is called precision health. That means every drug will be customized, every medicine will be customized for each individual patient at the site of delivery. That means inside the pharmacy, inside your doctor's chamber, in the hospital, every drug, every treatment will be customized for each individual patient based on their history, background, their symptom, and their infection level. Currently, we have like one set of antibiotics for all sorts of infection. But that's why antibiotic is working for one people. Same antibiotic is not working for me for the same set of symptoms, because I come with different level of resistance. I come from a different background genetically. So that type of treatment is called precision health and precision medicine, precision healthcare or precision medicine, also known as personalized medicine. And that is a sector where biomedical engineer, biological scientist, bioinformatics specialists, and genetic engineers will come together and work with doctors and other psychologists and behavioral scientists to find this type of solutions. So with that, and this was kind of repetition, I want to end here and open it up for question.
Okay, thank you, Professor Masud, for your wonderful presentation, starting from the very basics and going into the deep and into the multidisciplinary research area. This is a very nice talk. I think our students and faculty members benefited a lot from your presentation. So there are some questions, I think, in the chat box.
Yes.
So I can read out a few questions from there for
Okay,
you.
please go ahead. Yes.
The first one asked by Tahsin Asma Mim. She is our lecturer of Tripoli department. She actually wanted to know the PhD opportunities at BUET in semi-syn biofield. Or I think if there is any opportunity elsewhere, also you can talk on that.
So this is a very brand new area, and unfortunately, very limited number of top ranking universities have the manpower and resources to actually start research on this area. So our university, we are actually trying to develop this capability. As of today, we don't have any specific faculty member or research group that is doing on this. But at the end of this year, we are opening our new biomedical engineering department. And recently, we went through some academic reorganization. And part of the goal of this academic reorganization is to actually promote this type of research. So I'm hoping that very soon. Currently, we have very, very strong PhD program in our department. We have 120 PhD students. So we are hoping that we can open up PhD opportunities in this particular area very soon.
Okay, another question asked by one of our students, Sanjidul Islam. He wanted to know about the extraction of the binary 2 states from human DNA. He commented that expecting a more detailed description of how this could be performed, because we need just the binary zeros and ones from a range of DNA states. How can that be thought to define DNA states for only 2 states?
There are 2 possible scenarios. If you want to express it in a DNA state by a binary combination, then it will be computationally very difficult, and then you need to just to for each of the DNA state, you need to have many different binary bit combination. So you cannot express it by just two single bit. Typically, every bit of information is now expressed in a combination of binary bit. Just think about your keyboard. When you are typing letter A, is not actually one binary bit, it's just 8 binary bit combination is giving you letter A, right? So for each DNA state, then you need probably a long chain of binary bits to express each DNA state. And if you want to fully express all possible DNA state for a particular cell, probably you need thousands of long binary chain. So those are still at the theoretical research stage, so that one possible alternative is if we can implement multi-valued logic, come up with multi-valued logic function instead of Boolean logic function, then probably we can you can implement same DNA state with much lower number of multi-valued bits, because then each bit can have multiple different combination. So just by mixing and matching 3 different variables in ternary logic or quaternary logic, probably you can express a DNA state. But in case of binary bit, you probably need 8, 10, or more than 10 binary variable combination. So the other way is that you have to probably completely move out of this concept of expressing things in electronic signal. We are still thinking that those digital signals or analog signals we are expressing in terms of electronic voltage and current. That's how the electronics world are now working. We are expressing electrical signals, whether it's a binary signal or an analog signal, we're expressing signals in terms of voltage and current. But what if we can express it in magnetic state? What if we can express it in other state like biological signals, DNA phase? So that we are completely moving out of electronics. It will no longer remain electronics. So what would be the mode of expression? That is yet to be determined.
Okay, thank you again. Tahsin Asma has another question. What can be the challenges for research in neuromorphic computing and how to overcome them?
So the currently neuromorphic computing is actually almost a 3-decade-old research area. It first started with IBM Blue Chip project in almost 4 or 5 decades ago, but it is actually recently, and then due to the computational complexity, the amount of transistor they need to implement a simple small section of neuromorphic computing circuit, they actually abandoned that, because in 70s and 80s, the transistors were operated at 5-volt range. So they estimated that if they need 10 billion transistors just to implement one small portion of a neuromorphic chip, the amount of voltage it will ask for and the amount of energy consumption and temperature it will produce, no system can sustain that. So neuromorphic computing went to kind of in a sleep state for 3 decades. But after 2010, as people, different industry and academic organization, research organization started implementing ultra low power transistor working at sub voltage level, that is a fraction of a voltage level, now they're thinking that we can integrate now those hundreds of billions of transistors to mimic the behavior of neuromorphic computing. So all of a sudden, in the last 10 years, again, neuromorphic computing has become a very, very rich area of research. All the federal agencies in the United States now are heavily funding, particularly Department of Defense agencies are heavily funding this research because of the arrival of this ultra low power transistor technologies like graphene-based transistor technologies, nanowire transistor technologies, and other emerging 2D nanomaterial-based technologies. So in summary, neuromorphic computing research is going in two fronts. One, how to come up with a newer architecture beyond von Neumann computing model, where same cell can work as memory sometime, logic processing sometime. And the other form, whether it's memory cell or logic cell or combined cell, how can we implement each of these cell with a faster transistor that will ask for lower power, so that we can compact billions of transistors together to mimic the human brain behavior. So there are like multiple directions of research, and there are many universities across United States, European Union, even in Singapore and China, also in Canada, running this research on neuromorphic computing. And if you do a Google search, you can find actually many different professors. I really wanted to start a neuromorphic computing research, but as I am getting busier and busier in my administrative and leadership role, I am finding that I am becoming useless in research. But if you are interested, I can direct you to some of my well-established colleagues and young and promising rising colleagues who are doing research on neuromorphic computing.
Okay, thank you. Another question asked by one of our students, Niloy Kantipal. He wanted to know, is there any chance to reduce the waste of energy through the miniaturization technologies? That is, if we
actually,
technology.
The question to your answer is already embedded in your question. The
Yes.
answer to your question is already embedded to your question. So the main motivation to scale down or miniaturization of technologies from micro level to sub-micro level to nano level, now we are talking about sub-nano level, the main motivation is to reduce energy per logic operation. So what logic operation is dependent on what? Switching of the transistor. You are turning on or off the transistor, right? To produce binary ones and zeros, right? So every time you are turning on and off, for every on-off operation, if you can do it with lower power, that means per logic operation, you are consuming less power. So that is the biggest motivation to miniaturize the transistor size. And now, in addition to miniaturization, there, as I mentioned in one of the slides, they are changing the structure of the transistor. Conventional planar MOSFET to dual gate MOSFET to FinFET MOSFET to gate all-around MOSFET. So at one hand, we are making the transistor smaller. On the other hand, we are changing the structure of the transistor so that we can turn it on and off at a much lower voltage. So research and development are going in two fronts. The changing the size of the transistor, changing the structure of the transistor to make sure that we can turn it on and off at with a lower voltage. That is actually the main motivation to move the transistor technology from micro era to nano era.
Okay, another question comes from one of our students. She is interested to know more about semi-syn biofield. Can you say something?
So basically, just in addition to what I explained earlier, so in the semi-syn bio is called semiconductor synthetic biology. So what they're trying to do, they're trying to replace a semiconductor device with a biological cell, or they want to develop a semiconductor device that can mimic the behavior of or the operation of a biological cell. So it's a two-directional research. I think in the next several decades, the target would be to find semiconductor technology or device technology that can not fully, but to some degree mimic the behavior of biological cell. Why is that? Because if we want to move away from this semiconductor technology, that means we have to throw everything we use today, an entire IC industry, computing industry, and semiconductor industry, they have to start from scratch. That is not possible because the entire global community have become dependent on current technology, and we are increasing efficiency and speed and energy efficiency, but the infrastructure, the manufacturing process, the academic program, the human technical skill, all the CAD tools required to implement those design will become obsolete overnight if we want to throw the semiconductor technology. That's why during the transition phase from one great technology to another great technology, there is a transition phase of several decades when they try to remain on the existing technology platform, but achieve the behavior or some part of the behavior or the benefit of the newer technology using the current technology. So that's where I believe research is going in the near future. But ultimately, probably if they can implement biological computers, then probably we'll see a completely new type of application, new type of device. Probably we can have a small computer device embedded inside our ring, and we can display it like a holographic memory in the air or on the surface of our palm, virtual keyboard, we can type it on our palm. So these are all sorts of crazy ideas people are presenting in the different conferences, in this type of specialized conferences. But those science fiction.
Okay, thank you, Professor Masud, once again for your nice answers to our audience questions. And I think we can stop it here today.
Yeah.
And now it is the time to invite our respected Dean of the Faculty of Engineering, Professor Dr. ABM Siddiq Hussain sir, to say a few words as the closing remarks of this webinar. Sir is also the chair of this session, and also actually I wanted to give at first invite sir to say a few words, but later I thought that if I could invite him after the session, then on the session topics sir could also comment a few things because he has a huge experience, and sir was the former head of Tripoli Department of BUET and former dean of the Faculty of Engineering of BUET also. And for many years, sir is also involved with AIUB. And I worked with under his leadership when I was in AIUB from 1999 to 2003. And again, I joined here in this year, March 2022, and I found him, and sir is still very well fit to lead the Faculty of Engineering. Also, me and Masud also was the student of Siddiq sir when we studied BSc in BUET. So now I would like to invite Professor Dr. ABM Siddiq Hussain sir, Faculty of Engineering and American International University, Bangladesh, to deliver his talk. Closing remarks.
Thank you, Professor Masud Chowdhury. actually for his excellent presentation, informing us many things. I mean, the current status of electronics and also the future trends. All we learned from him, well, from his basic concepts. I mean, we are really benefited from his presentation. Particularly, well, the trends, the future trends of electronics. And the main constraint of CMOS technology that we have learned from him today, also we are all aware of this, the power constraint. The power constraint. Actually, if I recall, over the last 52, 53 years since my graduation in 1969, I have seen the growth of this whole electronics and what I see, the most fundamental is Moore's law, which has driven an exponential growth in 3 fields. What I have witnessed, I am still a living witness of these 3 technologies that happened over the last more than 50 years. In the field of computing, in the field of enormous data storage, and also in telecommunications. And as a result, today we have got a global internet of unlimited bandwidth, we should say. We have unlimited, enormous storage capacity on global clouds, and also things like IoT, wireless sensor networks, and the applications of data science, which are emerging technologies, we shall be using more and more. IoT, 5G mobile communications, and applications of data science. The constraint is power. So we have to design both structurally and also how we can reduce the power. The future lies in that. And also he has talked about environmental things. I mean, very, very useful information for us, where engineers will be more and more involved. You see, it's in different, and funding opportunities also he has talked about. And I am sure this presentation, his presentation was so excellent. I am really delighted the way he presented from fundamental concepts to latest research areas where we have to work, particularly our young faculty members and also our students. They have to give more attention to all these research areas. Well, we thought Moore's law will end, but no, it has not yet ended. It is continuing. From his predictions and the futures, I think similar research is going on in Georgia Tech also. I mean, where one of my former students, Asif Islam, then we heard one professor, his name is also, I think, in Georgia Tech, Professor John D. Kressler from Georgia Tech. Maybe Professor Masud Chowdhury may recognize them. So all of them, they are now working in this low power area, low power devices, ultra low power devices, and which is the technology or research trend.
Yeah.
I'm sure that his presentation will help us will help us. He has given a lot of guidelines in different areas. And lastly, I would like to thank the organizers, particularly Professor Muhibul Haq Bhuiya, who has hosted this session very well. And in future also, we can talk about, initially he talked about future research collaboration or also collaboration between our two institutions. So Professor Muhibul Haq Bhuiya can continue with these things, because we can always communicate with him, and whenever he visits Dhaka, we invite him to visit our university. We have now a lot of facilities at this university, located in a in a good area, in good location of Dhaka city. So I will invite him to visit our university whenever he comes to Dhaka next time. Once again, I thank all of you, those who attended this session, and one request from the participant came to share his presentation slides. I hope that he will do it through Muhibul Haq Bhuiya. So anyone interested may contact, I think, Professor Muhibul Haq Bhuiya, if they can learn something more from his presentation slides. So thank you very much once again, and good night. Good night to Professor Masud, and good afternoon to everyone in Dhaka.
Thank you. Thank you. It has been a wonderful experience, and I am really grateful to all of you. And I just want to say one last thing. For our university, Bangladesh is now a top priority country to bring new students, and we are open to signing different types of memorandum of understanding with universities in Bangladesh, both private and public. So I will keep in touch with Dr. Muhibul and other in the leadership position, including Dr. Siddiq sir. And students, anytime you want to apply to our universities in any program, don't hesitate to email me. I will try to make it as easy as possible for you. Thank you.
Okay, thank you, Professor Masud, and also our respected Dean sir for your speeches. Now it is the time to show some plaque of appreciation to our speaker. So I can just share it because this is virtual. So the appreciation is also virtual. So actually this is the banner and the bio abstract that we given. Now this is the plaque of appreciation. Dr. Anwarul Abedin lecture series, the plaque of gratitude, given to Professor Masud Chowdhury in recognition of the valuable contributions as a speaker at this webinar. So thank you, Professor Masud, once again. I will share this slide also with you via email. And this is the certificate of appreciation prepared for you from the Faculty of Engineering of American International University, Bangladesh, for your valuable contribution to this webinar. And this is signed by our respected Dean Sir, Professor Dr. A.B.M. Siddiq Hussain, Dean, Faculty of Engineering, AIUB, our respected Honorable Associate Dean of Faculty of Engineering, AIUB, Professor Dr. Muhammad Abdur Rahman, and our Honorable Vice Chancellor, Dr. Carmen J. Lamagna of AIUB. So thank you once again for your deliberation to this webinar and agreed to be a part of this webinar. So thank you all for being present here.
Thank you.